Hi everyone, am I audible? Okay, so let us start then. So today we will be talking about some greedy algorithms. We have already learned about DP. In dynamic programming, I told you that we have to come up with a recursive substructure, and then there are concepts of states, and then there are concepts of overlapping subproblems, right? Greedy problem, what is a greedy problem? It is something where there is a type of greed. So greed means that given a question, you might realize that every time I have to look out for the current maximum in the array, or every time I have to look out for the current minimum in the array. So such kind of thing is called as a greed, which drives your solutions. So what I'm going to do is I'm going to take the very first problem, and it is a very well-known greedy problem, very frequent in interviews. So it says that we have been given n activities. Okay. And for each activity, there is a start time and there is also an end time. Okay. So there is a start array of size n, end array of size n, containing the start and end times of the n activities. Now there is a rule. The rule says that you can perform only one activity at a given time. It means you can't do multitasking. So at time t equals to t naught, you can just involve in one activity, not in multiple activities. Okay. So given this input, you have to tell me, you have to find maximum number of activities that may be performed. Okay. And you can perform these activities in any order, let me tell you. So it is not necessary that you have to first perform the first activity and then perform the second activity and then perform the third activity. You can perform these activities in any permutation, in any order. The only thing to be kept in mind is that at any point of time, you cannot engage in parallel activities. Is the question making sense to everyone? Yes or no? Okay, so let's say the start and end times of the activities are given to us. And for the first activity, the start and end time is 1, 6. And for the second activity, it is 3, 9. So what will be the answer in this case? So the answer in this case will be 1. You can only engage in one activity. So if you perform the activity that starts at 1, ends at 6, starts at 1, ends at 6, it means you cannot engage in this activity because its starting time lies in between this. While you are doing this, you cannot engage in that. Is it making sense to everyone, like how the output is 1? Yes, no? Right? Okay. Cool. Let's say now the start and end times, they are, for the first activity is 1, 6, and for the second activity it is 6, 10. So what will be the output in this case? Will it still be 1 or something different? Okay, so this is something where you have to ask me, hey, I mean, you have to literally question me that if somebody ends his activity at 6, can he immediately switch to another activity that starts from 6? I would say yes, that is possible. And because that is possible, I'm assuming that is possible. So both the activities in this case can be done. So the output over here is 2. Okay, one final example. What if the second activity has start time of 10 and time of 15? Any thoughts about this? Here, quite comfortably, both the activities can be done. So from 1 to 6, you do one activity, and from 10 to 15, you do another activity. There is no intersection at all. Okay. Let's take a bigger example now. Let's say the start and end times of the activities given to you are 3, 4, 0, 6, 1, 2, 5, 7, 5, 9, and 8, 9. Can you tell me what will be the answer in this case? So most of you are saying that the answer is 3. Can you also tell me which activities are you planning to do? Let's call the first activity as activity 1, second as activity 2, third as activity 3, and so on. So which activities have you chosen to do? First, fourth, and sixth. Anyone who realizes that more activities can be done? Instead of 3 more activities can be done. Anyone who realizes that? Ankit, according to Ankit, 4 activities can be done. Okay. Yeah, so the answer over here is 4, because what I can do is I can choose this as my first activity, which starts at 1, ends at 2. And then my next activity could be this, which starts at 3, ends at 4. And then my next activity could be this, which starts at 5, ends at 7. And then my final activity could be this, which starts at 8, ends at 9. This is the sequence that I can follow. And in the sequence, 4 activities are being done. And you will realize that no matter what other sequence you consider, you will not be able to perform more than 4 activities. So the answer here is 4. Is it making sense to everyone how the answer is 4? Yes, no? Yeah? Okay, great. So tell me, how do I solve this problem? Remember what I had said in greedy problem? There is some kind of greed that you have to figure out, and then you have to work with that greed. Okay, so Tanush is saying that sorting based on end time should help. Anyone else who thinks like that? Okay, so whenever you see such kind of problem, then you have to think that, hey, given this input, what is the first activity which you should do? So according to you, what should be the first activity to be done? I mean, what should be the property of an activity which makes it the first activity to be done? Min possible. What min possible? Okay, can I say that, hey, everyone look at the board. Can I say that it makes sense to first do that activity which has the smallest start time? So let us do that activity first, which has the smallest start time. Would it make sense? Yes, no? if you are watching it here itself, it does not make sense. Because if you take a look here, which activity has the smallest start time? You tell me. Second activity, because its start time is 0. If you do that activity as your first activity, will you be able to do other activities? Yes, no? You might be able to do, but you won't be able to do 4 activities for sure. Is it making sense to others that why picking the activity with the smallest start time might not be helpful? And how about others? Would you care to respond? Okay, so as a quick example, we can see that let's say there are certain activities with given start and end times. Let's say this is your first activity, that's your second, that's your third, and that's your fourth. What will be answered in this case? What is the maximum number of activities we can do in this case? And what are those 3 activities? Second, third, and fourth, right? Okay, so you would choose to do this, this, and that. Okay, now if you stick to this rule that, hey, let's first do that activity whose start time is smallest, then you would have done this activity. The moment you would have done this activity, you would not have been able to do any other activity. Correct? And why is that happening? It is happening because the activity with the smallest time might have a very large end time. I repeat, the activity with the smallest time might have a very large end time. And that being the reason you might not be able to choose any other activity. So it is not a right greed to say that, hey, we will first pick the activity with smallest time, because its end time could be very, very high, could be infinite. Does it make sense? Yes or no? I hope it should. Okay, cool. So now that we understand this idea, what else to do? So the first greed fails. The second greed that a lot of people come up with is they say that we should do that activity which has smallest duration. Which has smallest duration. So duration means difference of end and start time. What do you think? Is this greed going to help if you pick the activity that has the smallest duration first? Yes, no? Let's quickly take a look. Let's say the start and end times of the activities are like that: 9900, 110, 1560, 6590. Okay, which activity has the smallest duration over here? The first one. The duration is just 1 unit. 100 minus 99 is 1 unit. If you do this activity, you won't be able to do any other activity because it starts at 99, ends at 100. Okay, so let's say if this is your first activity, starts at 99, ends at 100. Okay, and now just hold on. Even if you do this activity, it may be possible that you are able to do first activity. Yes, you will be able to do that, which starts at 1, ends at 10. You'll be able to do this also, starts at 15, ends at 60. And you might be able to do this activity also, which starts at 65, ends at 90. Okay, cool. So it looks like in this particular example that might work, right? Do you understand that this example is not giving us a counter example? Here, even if you do the first activity, you might be able to do the other activities. Does that make sense? Right? Okay, but still, can somebody think of a case where this might not work? It is guaranteed that this is not going to work. It's just a matter of coming up with a case. Anyone who can come up with that? Yeah, there are a lot of examples. Let's say, and then okay, tell me what should be the answer over here? What is the maximum number of activities that we can do? Two activities, right? And what are those two activities that you have planned to do? 17 and 820. But if you stick to agreed that you would first do an activity with the smallest duration, in that case, you will end up doing this. And when you do this, which starts at 5, ends at 9, you will not be able to do this because this 17 has an intersection. Similarly, this 820 also has an intersection. So this grid is also not right. Cool. Now let's think about the correct approach. Do you see one thing? That if you have to actually perform certain activities one after the other, then you have to ensure that the start time of the next has to be greater than or equal to the end time of previous one. So let's say this is your ith activity and this is your I plus 1th activity. Then the start time of I plus 1th activity has to be greater than or equal to end time of ith activity. Should this thing hold? Yes or no? Very well. This thing should very well hold. And you can see it in action that the start time 3 over here is greater than or equals to 2. And the start time 5 over here is greater than or equals to 5. 8 over here is greater than or equals to 7. Yeah, this has to be ensured. Now, think properly. You will realize that you should try to free yourself as fast as possible. Because if you are free, then you have the time, you have the bandwidth to do other set of activities. So it makes more sense to do that activity first, whose end time is smallest. Whose end time is smallest. So let us first pick the activity with smallest end time and then move on. Is it making sense to others? Yes or no? Right? So it looks like this is going to be the right grid. So what we will do is, see, one approach is that you look at this array, figure out the activity with the smallest end time, and then figure out the activity with next smallest end time, and then next smallest end time, and then next smallest end time. But a better way could be, hey, first sort it based on end time. If you sort this data based on end time, then it will be easier. Do you feel so? Yes or no? Yeah, for sure. So if you sort these activities based on their end time, the first activity which you will get is 1, 2. The second activity will be 3, 4, then 0, 6, then 5, 7, 8, 9, and finally 5, 9. Okay. Now you would say that, hey, let this be my first activity. Okay. Now, if you have currently done an activity, listen to it very, very carefully. If you have currently done an activity, you should remember its end time. Because if you do not remember its end time, you will not be able to decide whether the next activity can be done or not. Like here, the end time is 2. Then the end time is 2. So when you move on to this activity, you realize, hey, this can be done. Why? Because its start time is greater than the previous activity's end time, which I did. Right? Do you see that start time is not sorted? It's just that end time is sorted because you have sorted this data based on end time only, correct? So after doing this activity, when you move here, you realize that, hey, this can be done. And now you remember its end time, which is 4. Now, when you come to this activity, which is third activity, will you be able to do that? Yes, no? The answer is no, because its start time is 0, which is smaller than the end time of previous activity. And then you come here. Will you be able to do this? Yes, because the start time 5 is greater than the end time of the previous activity that you had done. Now remember this 7. Now you come here. Can this activity be done? Yes, again, because its start time 8 is greater than the end time of previous one. Can this be done? No. So it turns out that you have chosen the maximum number of activities that you could do just by sorting this array based on n time and picking first activity and then picking all the subsequent activities by tracking the end times. Is it making sense? How many of you are clear with this approach? Yeah. Okay, great. Okay, however, there is one important thing that you guys should be asking me. I have waited for you to ask, but no one has asked it so far. It's a good question to reflect upon. See, sorting based on end time makes a lot of sense. Why we have discussed that. But do you realize that in my algorithm, I am always picking the first activity? No matter what data I have, after sorting, I am always picking the first activity. Do you notice this thing? Yes or no? According to this algorithm? Yeah. So my question to you is that, hey, is it necessary? Listen to it very carefully. Is it necessary that the combination of activities which leads to your answer will definitely contain the first activity? Is it necessary? So for that, let's take an example. Let's say the activities are like 1, 4, 3, 7, 9, 11, 13, 50. This is your first, second, third, fourth activities. What should be the answer over here? And what are those 3 activities? One, 3, and 4. Okay, good. So you are planning to do this activity 1, 4, and then this activity 9, 11, and then the final one. Okay, can there be some other combination? Yes, 2, 3, 4 is also a combination because I can choose to do this as my first activity and then this and then that. So my answer continues to be 3, but the combination has differed. So do you realize that there can be multiple solutions, as in there can be multiple combinations? Yes, no? Right? So this was first thing that I wanted to make you realize. But my actual question still remains the same. My actual question is that, hey, can it ever happen that the combination of activities that leads to your answer does not start from the first, starts from second or third? Can it ever happen? Because currently my algorithm assumes that the combination of activities will start from the first one. Give me one moment. Is the screen visible to everyone? Can you guys confirm it quickly? Yes, no? Yeah. Okay, great. Yeah. So coming back to my original question, my question was that is it necessary that the combination of activities which leads to our answer will always start from the first activity? Just hold on once more. You guys can keep thinking the question that I have asked you guys to think for. Meanwhile, let me fix certain things. Okay. So, yeah, I think one of you is suggesting an answer. So you are saying that we can always choose first because n time of next will be larger. Okay, okay. Okay, let's talk about it. This is a very important thing to know about this problem. Tell me one thing. Let's say you have sorted your activities based on n time. That is the first step. You have sorted your activities based on the n time. So you got certain activities with you after doing that. Okay, so let's say you have an activity 10:15, and then somewhere you have an activity 16:22, and then somewhere you have an activity 24:30. Okay, now just keep looking very clearly. Let's say the combination of activities leading to your answer does not start from the first activity after sorting based on n time. Rather, it starts from here, and it was this, that, and that. Can I say that no matter what combination you are considering, in that combination, its first activity can always be substituted by the actual first activity? Can it always be substituted by the actual first activity? The answer is yes. Why the answer is yes? Because we know that this 15 has to be smaller than that 16, and this 22 has to be smaller than equals to that 24. Now, the activities are sorted based on n time. Because activities are sorted based on n time, so it is guaranteed that whatever n time you will get here will be smaller than this n time, smaller than or equals to 15. So even if you do this activity, you will be able to do this activity. See, you will be able to do this activity only if the previous activity had an end time which was smaller than or equals to this, which is present in this case. But it is guaranteed that it can be substituted by the first activity, because the first activity will definitely have an end time which is even smaller than 15, which implies even smaller than 16. So the first activity here can always be substituted by the very first activity. Is it making sense? How many of you get this point? Just type in yes or no. Yeah, too simple to understand. So it just means that you can have multiple answers. Like in this case, one answer that you have is this, that, and that. But there will always be another answer which starts from the first activity also. Like here, you can substitute this thing by this thing, because this 7 is larger than this 4. So if you could do 9 after 7, you can do 9 after 4 also. Correct? So this is the proof of correctness of this algorithm. Okay, how many of you can code this idea now? This problem is very well known as activity selection problem. You can read about it whenever you go back. You can learn about it from your dashboard as well. It's present there. What will be the time complexity of solving this problem if there are n elements? It will not be n, it will be n log n, because first you have to sort, okay, which is going to consume n log n time. Let's move on to another problem. So it happens with a lot of people when they, in Renaissance, almost hundreds of people have told me that when they learned greedy section, their brain started working better. And that happens because in such questions, you constantly have to look for why this approach and not that approach. Okay, so it's a great thing to learn to improve your understanding of algorithms. Okay, So we have a question saying we have been given n items. Okay. And for each of those items, there is a price and the item itself has a weight. Okay. So there is a price array of size n and a weight array of size n. You have been given another integer w. This w indicates the capacity of a bag. So think like there is a thief and that thief has a bag. The capacity of that bag is to hold w kgs of weight, not more than that. And now that thief entered into a house, and in that house there are n items. Every item has a price and a weight associated with it. Now what I want is, I want to take away some items. The thief wants to take away some items such that the total price is maximized. This is what is to be done. An important thing that I would wish to tell you over here is that an item may be broken. So if you are not able to take an item completely because you do not have enough space, you can break it and take half of it, 1/3 of it, 5/9 of it, 7/11 of it. It is up to you. So let's say there is an item whose price is 20 and weight is 4 kgs. Now, if because of some reason you are not able to take 4 kgs of weight completely, because let's say its capacity was 2 kg only, then you can break it from here and take half of it. But tell me, if you take half of it, how much price will you get? It should be in proportion with the weight. Yeah, it will be half of it, which is 10. You will get 10. So is the question clear to everyone now? There is a thief having a bag of a limited capacity W, and then there is this array containing price and weight of n items. So you can break an item if you can't take it completely because of some reason. What you have to do is you have to maximize the price of the items that you take away. No, you cannot take the same item twice. For every item, there is only one instance of it. Okay. Problem makes sense to everyone? Yes, no? Okay, we will quickly take a certain example. You know, this problem is very well known as fractional knapsack problem. And it has a variation of dynamic programming also, which is called 0-1 knapsack, which is there on your NSA dashboard. So those interested, very much interview specific problem. I mean, in every 4th or 5th interview that I get to know, they ask this question in their online coding round itself, which gives you a ticket to interviews. Okay, cool. So let's say we have been given prices and weights, and they are like 25, 10 to 40, 20. And now the weight of your bag is 21. For this input, what should be the output? Okay, one of you is saying that the answer is 44. Anyone else having some other answer? 84, 44. Okay, it will be great if you guys also mention which items you have taken and how much of that item you have taken. Have you taken it completely, or if you have taken a certain fraction? If fraction, then how much fraction? Please mention that in the chat box. Okay, there are different answers that different people are getting. Okay, so I'll not tell you what the answer is. Those of you who would have tried it at the best of your abilities would have found it out. I'll discuss the approach, and in the process of that, again, those of you who listen sincerely will be able to find the answer out. Okay, so let's forget about what is the answer for this test case. Can you tell me what should be your approach in general? Or what is the first activity, what is the first item that you would choose? Weight of maximum price. Second item. Okay, don't tell me first or second. Tell me like what should be the property of item that you should take. So Bhavesh is saying costly item. Okay, so let me stick to it. So can I have a grid? Look at the board, everyone. Can I have a grid that says highest price first? So basically it says that whichever item has the highest price, let's take it first. Can I have a grid of this kind? Yes, no? A lot of you are saying no. So let us see what happens if I stick to this grid. If I stick to this grid, then this is my bag having a capacity of 21 units. Now, according to this grid, what will be the first item which you will take? Whose price is highest? This has the highest price of 40 rupees. So you will take this. And when you take this, you have already filled your 20 units. But yeah, you have gotten 40 rupees with you. So let me write it here. Now you just have 1 unit of space remaining. So, so you have already taken this and your strategy is highest price first. So out of the remaining 2, the highest price is for this. So now you'll take this. When you take this, will you be able to take this completely? The answer is no, because the remaining capacity is 1 unit only. So how much of it you can take? You can take a fraction of it, which is 1/5 of it, right? When you take 1/5 of it, how much money will you get? See, its weight is 5, remaining weight is 1. So you can just take 1/5 of this item. When you take 1/5 of this item, the price that you will get is 4 units. So you will make 44 rupees by doing something like that. Is it clear to everyone that how is it 44? Okay. Cool. You know, certain people who come up with this grid that highest price first, this might not be a right grid. Why it might not be a right grid? Because item whose price is highest, it can have a very high weight. It can have such a high weight that you are not allowed to take other items. Do you understand my point? It can very well happen. So let's say you are picking an item with a very high price, whose individual price is very high, but its weight is so high that you are not able to take anything else. Okay, but in reality it can happen that instead of taking this, if you would have taken certain other 5-6 items, then their combined price would have exceeded the price of the costliest item. Do you see what I'm trying to say? Yes or no? Right? So that is exactly what can be the case over here. So, you know, here what makes more sense? Here it makes more sense that, hey, In reality, you want two things. You want to increase the price that you are going to get. You want to always increase the price that you are going to get. And so I'm writing proportional, and inversely proportional I'm writing. You want to reduce the amount of weight that you want that item to contribute. So see, the best item could have been that whose price would have been infinite and weight would have been 0, isn't it? So picking that item would have mean you get infinite wealth without letting go of any weight from this bag. So I need two things, not just one thing. First thing is that very high price, and second thing is a very low weight. So it makes more sense that, hey, let us give more priority to that item whose P by W is highest. Price per unit weight is highest. Is it now making sense to everyone? Yes or no? Yeah. So what you can do is you can sort this data based on P by W. So when you sort this data based on P by W, this comes first, because for this P by W is 5. And then comes this, for which P by W is 4. And then finally comes that for which P by W is 2. Correct? Now you can start taking the items. So always take the first item, then take the second item if possible, then take the third item if possible, and so on and on. So can you tell me what will be the answer in this case? No, you will not get 44. How will you still get 44? You are not doing proper calculations. The correct answer is 58. I want you guys to try it again. Now, this is a very simple 7th, 8th grade maths problem. You should be able to solve that. Okay, those of you who have solved, good. So the first item that you will take will be this. When you take this item, you get 10. You get 10 rupees with you. Just hold on. You get 10 rupees with you. Okay. And also you have used 2 units of space. When you have used 2 units of space, the remaining space is 19. Now, can you take this item completely? 19 units of space is remaining. The next item has 5 kg weight. So can it be taken? The answer is yes, because 5 is smaller than that. When you take this entirely, you will get 20. And the remaining space will be minus 5, which is 14. Now, can you take this item completely? No, because the remaining weight is 14 and this item has a weight of 20. So how much of it you can take? You can take a certain fraction of it. And what is that fraction? Tell me the fraction. 14 by 20. Its total weight is 20 and you are able to take 14 parts of it. So out of these 20 parts, you can just take 14 parts of it. So in this proportion, you will get the amount. And what will this amount be? 28. So what will the overall sum be? 28 plus 20 plus 10 is 58, and that's your answer. Is it making sense to everyone? Yes or no? Okay, good. Cool. So this question can easily be solved using by first sorting based on a certain criteria, which is P by W. The important thing that I want to understand over here is that the greed over here was P by W. So in problems which are greedy in nature, you have to figure out whether I have to sort based on P, whether I have to sort based on W, whether I have to sort based on P by W or P into W. So these are the things that you have to think and then decide. That is the very nature of greedy problems. So I won't consider any further greedy problems. You can look at your dashboard. There are plenty of them and they're interesting at the same time. They're very, very helpful. Cool. We'll move on to something else. But did these 2 examples give you an idea of what greedy problems are and how do we deal with them? Yes, no? Yeah, very interesting. Cool. Let's move on. You know, there is a data structure which is specifically meant to help us to solve greedy problems. And what is that data structure? It is called as heaps. Why? Because the nature of this data structure is such that it can very easily give us current max or current min. This heap is also called as, technically heap is just a loose name, but technically it is called as priority queue. And it has got nothing to do with the normal queue, which is first in first out. It has got nothing to do with that, at least when you think mentally. But yeah, it is called priority queue because it prioritizes maximum element over non-maximum elements, or minimum element over non-minimum elements. Have you guys heard of it? Priority queue? Yes, no? Okay, irrespective of whether you have heard or not, we will learn about it in detail. Okay, so I have already talked to you about some hierarchical data structure like tree. How about a simple array? Let's say there is an array, and forget about index 0 for now. I am ignoring index 0. Let's say the indexes are, this is index 1, 2, 3, 4, 5, 6, 7. Would you say that array is a hierarchical data structure? Does it sound wise to say so? No, it is a linear data structure, right? But the reality is that if you use your brain properly, you will be able to consider this as a hierarchy also. And it's very interesting. Hierarchy means that parent-child model has to be there. Now you might be wondering that, hey, what is the parent here and what is the child here? So I would say, hey, just think that 1 is your parent and it has a left child of 2 and right child of 3. Okay. 2 has a left child of 4, right child of 5. 3 has a left child of 6, right child of 7. Okay, at this point, this diagram looks very, very convoluted. You might not be able to even realize it. But if you write it on a piece of paper, you will be able to see, hey, it completely looks as if it is a binary tree. Because now if I write it, I'll say this is my root. So let me write it here. This is 1. And now this has a left child. What is that left child? Left child is 2. And it has a right child, which is 3. Now looking at 2 again, it has a left and right child of 4 and 5. And similarly for 3, they are 6 and 7. Do you understand how I'm modeling an array as if it is a tree, binary tree? Yes or no? Yeah. You know, using this particular logical modeling, you can treat an array as if it is a tree. See, it is an array only. This is just your mental modeling of array. This is all in your mind. The reality is that data is lying in array only. Okay. Now, if you just imagine this is how data is lying, you can write certain algorithms on it. And those algorithms that you will write will correspond to a heap. You will be able to basically create a heap. And that heap data structure will very efficiently get minimum and maximum for you. Okay, but before that, let's look at some terminologies. So see, these things are indices. 1, 2, 3, 4, 5, 6, 7 are all indices. So if my current index is I, what will be the index of left child and right child? Okay, one of you is saying I plus 1 and I plus 2. Then for 3, it would have been 4 and 5, but it is 6 and 7. 2 into I and 2 into I plus 1. Does that look good? That looks totally good. So the left child is 2 into I and the right child is 2 into I plus 1. So you can see for 1, it is 1 into 2 and this is 3. For 2, it is 2 into 2, and this is 5, and so on and on. Is it clear to everyone? This was the first basic thing to understand. Now, if let's say there is a node whose index is j, then what will be the index of its parent? The index of its parent will be j by 2. In fact, floor of j by 2. And that is very easy to guess, isn't it? Because if the parent is 2i, sorry, if the child is 2i, the parent will just be half of it. And half of this will also be this, because you are taking a floor. So think, if you perform a division by 2, 1 by 2 will be 0, its contribution will be gone. So I can say if the child that you're talking about has an index of j, then parent will have an index of j by 2 floor. Does it make sense? Yes, no? Okay. Now tell me one thing. When you model an array as a tree, can it ever happen that you get a tree that looks like this? Can it ever happen? The answer is no, it can never happen like that. Why it can't ever happen like that? Because see, when you are modeling that array like this, then you have got index 1, index 2, index 3, index 4, index 5, 6, 7. And now indices come in a sequential fashion in an array. Can it ever happen that there is an array in which index 4 is not there, but index 6 is there? Is it possible? It's not possible. So when you are saying that there is an array whose representation of tree is like this, then it's nonsense, because you are saying that index 1 is there, 2 is there, 3 is there, but 4 is not there and 5 is there. Then 6 is there, 7 is there, and then 8, 9, 10, 11, 12, 13, they are not there, but 14 is there. So it means that when you model array as a tree, it will be a complete tree. Now I need to define complete tree. Complete tree is that in which all levels are full except the last level. See, it can happen that the last level is not full, it is partially full. So let us say you had an array. So you had index 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you model this as a tree, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. All the levels are full apart from the last level, which is partially full. So this is the property of the tree. It will be a complete tree. Does it make sense to everyone? Yes, no? Yeah. Moreover, in the last level, all the nodes will come as left as possible. So it will never happen that the first node is here and the last node is somewhere there. No. So there is no discontinuity. For sure, there will be no discontinuity at all. Okay, now I'm asking some brain teasers from you regarding this tree. So is it correct to say that all non-leaf nodes have exactly 2 children? All non-leaf nodes have exactly 2 children. Is it correct to say so for such a kind of tree? Okay, a lot of you are saying yes, one of you said no. Still thinking about it. Okay, so the real answer is, what if your array was of size 10? If your array was of size 10, then you would have had 10 coming in over here. And here this 5 is a non-leaf node which has 1 child only. It does not have 2 children. So it can happen that there is a non-leaf node but instead of having 2 children, it only has 1 child. Does it make sense to everyone? Yes or no? Why it can happen? Now, I can say one thing for sure, that at max, there will be only one such non-leaf node, which has 1 child. It can never ever happen that there are 2 or 3 different non-leaf nodes having 1 child only. Like if you say that, hey, this is possible, this is not possible, because after 10, 11 must have come. And the moment 11 has come, that means 5 is not in that category, only 6 is in that category. Does this point also make sense, that at max there can be only one such? Yeah, okay, cool. Having acquired this much of knowledge, let's come back to heap. So there are 2 kinds of heap. First is a min heap. What is the property of min heap? Very simple property. Every parent has a value which is smaller than or equals to both children. Both means left and right children. So you can read this property, very simple to read. For every parent, it's both the children should be greater than or equals to the parent itself. So tell me, is this a min heap? Yes or no? The answer is yes, it is a min heap, because here 2 is smaller than both the children, 6 is smaller than both the children, and 10 is smaller than 15. It just has 1 child. Okay. Similarly, you have got max heap. Max heap is the reverse of it, in which every parent is greater than or equal to both the children. So let's say you have 20, 12, 7, 10, 3, and 4. Is this a max heap? Yes, no? Okay, great. Now, if let's say you are considering a min heap, which element will be the minimum element? Root will be minimum element, correct? Similarly, if you are considering a max heap, what will be the maximum element? Root will be the maximum element. You know, this very property of min and max heap makes it very easy for us to find out what is the current minimum or what is the current maximum, depending upon whether your heap is min or max. Does it make sense to all? So now the question that should cross your mind is, see, let me tell you one thing first. In all the languages, there are some default implementations of priority queue. You do not have to implement your own heap. You can just import the library or include the library STL or collections or whatsoever, and you can use the priority queue. Some people say in certain languages there is no provision of priority queue. So I would say that, hey, you don't need to worry about that, because there will definitely be some other data structure which will behave like a priority queue, because it is so important that you cannot deal with your computer science without having priority queue. So priority queue is present in almost all the languages. You just have to explore the library and how to use it. Okay, cool. So now let's say your interviewer asks you that, hey, I'll give you an array containing some elements, and now you convert that array into let's say max heap. Convert that array into a max heap. So for that, what I'll do is I'll consider a sample array for now. Let's say we have got some random set of elements, 0, 10. Let me write it here. I'm going to erase this part. I hope it was clear. So you have got 0, 10, 12, 9, 8, 3, 11, and then 7, 6, 5, 4, 1, 2. This is your array. So what do you think? If you represent this array as a tree, will the structure be of a max heap? Yes or no? Just represent it, draw it on your piece of paper and see for yourself whether it turns out to be a max heap or not. So your first index is this 0, has a left child 10, right child 12. Then comes 9, 8. Then comes 3, 11. Then comes 7, 6, 5, 4, 1, 2. Is this a max heap? Yes, no. This is not a max heap. Okay. So how to convert it into a max heap? Can you think of some approach to convert it into a max heap? Very good. Sorting can be one very simple way to do it, right? But whenever you sort something, it takes you n log n time. So instead of sorting, can I do something else? Okay, so now we are going to talk about a very, very important operation on heaps, that very important concept that helps us to create a heap, max heap or min heap. Okay, I would say forget about this for a while. Okay, when looked independently, is this thing a max heap? The left subtree? Is right subtree a max heap? Very good. Now there comes a random person, which is 0, a random parent. Now, can I do something, some small number of operations on this thing to ensure that this gets converted to a max heap again? Can I do that? Okay, so what should it be? Think of that and let me know. Shift 0. Okay, of course we'll have to shift 0, but where do you want to shift it? What is your last here? And when you shift it to last, what will be your new root? You cannot leave vacancy for the root. Okay, so let's talk about that. So guys, whatever we are learning is based on the fact that our left subtree and right subtree, they are already max heap. The bone of contention is this root. So how to deal with this root? Tell me one thing, what is the property of max heap? The property of max heap is that every child is greater than equals to both its children, right? So you have to fix this parent. What is the best way to fix this parent? The best way to fix this parent is to swap it with either of these. Now in this scenario, what will you swap 0 with? Will you swap it with 10 or will you swap it with 12? You would want to swap it with 12, which means you will swap with greater of the two child. Look at both the children, whichever is greater, swap this with that. So when you perform a swap, 12 comes here, 0 comes here. Is it fair to say that now the job is done? Now this entire thing is a heap? No, it's still not fair to say. But is it fair to say that because you have done a swap operation with right subtree, so left subtree is undisturbed, no need to touch it, right? Okay, cool. So now left subtree is undisturbed, this root is happy, so you should now move from here to here. So when you have done this thing as your first step, your next step should be to move to the subtree that is disturbed or that you swapped this with. Now you'll come here again. Now you'll realize that, hey, if you forget about this much part for a few moments, imagine it is not there, remove it from your field of view. If you just look at this, the situation is the same. How? If you only look at the left subtree, is it a max heap? Is it a max heap? 3, 1, 2. Yes. If you only look at the right subtree, is it a max heap? Yes. Right? So come back. Now again, the same thing needs to be done recursively, which means again figure out the max of the two children, which in this case is 11, and swap that with this. So 11 comes here and 0 comes here. And now again in this process, you have not disturbed the left subtree, you will only come to the right subtree. And now you realize that, hey, here there is nothing below it, so leave it as it is. Now this entire thing has been converted into a max heap. Does it make sense? How many of you got the idea? Simple, isn't it? Okay, great. So what I want you guys to understand here is that this idea can be used very easily. Now, if you want to use this idea, these are the only two things that you have to do. And you have to keep doing these two things until you reach a node, which is a leaf, because if something is a leaf, then there is nothing below it. But for this idea to work, you have to ensure that if you are planning to make, let's say, there was a big tree, and in that, let's say there is a small subtree, and you are planning to make that small subtree into a heap. For that to happen, you have to ensure that its left subtree and right subtree are already heaps. This has to be ensured, otherwise this algorithm won't work. Is that clear enough to all? Yes or no? Okay. So how to even initiate this algorithm? Because this algorithm requires that something should already be a heap, right? So let's take a quick example. Let's say you have got 10, 20, 30, 40, 50, 60, 70. Is this a max heap? Yes or no? This is not a max heap, right? Now I want to make it a max heap based on whatever we have learned so far. So how can I do it? Whatever we have learned, can we do that operation directly at this? No, because left and right are not already subtree. Tell me what kind of subtrees, when looked at individually, are already max heaps. What kind of subtrees? Leaf nodes, very good. Does it make sense to all? If you look at the leaf nodes, they are already your max heaps. So what I can say is, hey, start your operation from here. So do your operation here, 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 here. But it does not make sense to do any operation there, because a tree in which there is only one node, that is already a max heap. So nothing is to be done. So it makes sense to start our operation from the last non-leaf node. Start your operation from the last non-leaf node. Now tell me, what is your last non-leaf node over here? It is 70. Okay. When you look at this 70, you realize that left and right are already heaps. So now what you will do is, you will apply the algorithm that I had written over here a few moments back. You'll figure out of these two, which is the greater one. It is 150. So you'll swap 150 with 70. That way 150 comes here, 70 comes here. And now after swap, you used to come to that part which you have disturbed, but now you realize this is a leaf, so nothing is to be done. Okay, so I told you, start your operation from the last non-leaf node and then move on to this. The same thing you will do here. For this, out of the two children, the greater one is 130, so you will swap it with that, and 130 comes here and 60 goes there. And then you come from here to here, realizing nothing is to be done. And then you come to the next non-leaf node at 50. And you realize the greater one is 110, which you bring here. and put 50 here. Now you come here. The greater of these two is 90. You put this 90 there. You put this 40 here. And you come from there to here, realizing nothing is to be done. See, what is happening is you are traversing across the non-leaf nodes from down to top in left to right fashion. Why? Because when you are traversing in this fashion, by the moment you come here, it will be guaranteed that the left and right are already converted into max heaps, which was the requirement. Does it make sense? Yes or no? So now do this process at 30. How many of you can do this same process at 30, which we have already done at several other nodes? Tell me, what should be your first step? Yeah, swap it with 150. The greater of the two child is 150. So you will swap 150 with that. And then what will be your next step? Will you leave? No. You will come to the disturbed part. Here again, what you will do? Out of these two, which is the greater one? 140. So you will swap this with 140. And then 30 comes here. And then you will come to the disturbed part, realizing nothing is to be done because it is a leaf. Cool. Now from here, you come here at 20. What will you do at 20? Out of the two, the greater one is 110, which is to be brought here, and 20 is to be pushed here. Now you come to the disturbed part, and again the greater one is 100, which you swap. And when you come here, it's already a leaf. Do you see again, by the time you come at a parent, at a node, you have already converted its left and right into heaps. The same operation you can do at this 10 as well, and this entire thing would have been converted into a max heap. Is it making sense? How many of you feel that this is quite intuitive, quite intelligent way to convert an array into a heap? Yes, no? It indeed is. So this is how a simple array gets converted into a heap. Okay. Cool. Now how to do it programmatically? So I would say, I'm not going to write the entire code for you, because after this much of discussion, you should put some brain to it, should try doing it on your own. And for code, you always have your dashboard where I have written the code extensively. But I would really urge you guys, before you look at my code, please give best from your side, okay, to convert an array into a heap already. And then there are certain operations which are associated with heap, okay. So those operations are again very easy to implement. Let's talk about some of those operations. The very first operation that you have on heap, that is called as get min or get max. So let's say there is a heap that looks like 10, 4, 7, 1, 2, 3. Is this a max heap? The answer is yes, it is a max heap. Now, if somebody asks you, hey, get max. If somebody says get max, then you just have to do return of array of 1. Why? Because this element is at index 1 of the array. So I'll just return array 1. As simple as that. Yes or no? Right? Okay. So this is how get max is executed. Very easy. Second operation is insert a new element x. Insert a new element x. Can you think of how to insert a new element? Let's say you want to insert 15. See, I told you at the very beginning, this is just a mental model. The reality is an array. Okay. So if you want to insert a new element in an array, you will insert it at the next slot. The next slot would definitely be there after the index of 3. So you have to put that 15 over here. But will you put 15 over here and relax, saying that, hey, what we have is again a max heap? The answer is no. So what will you do? What you should do is you should bubble up the new element. What is bubbling up the new element? Let us understand it quite clearly. All that you'll do is you'll compare it with its parent. And if the parent is greater, let's say if instead of 15, it was 5, then could you have relaxed? The answer is yes, because this 5 is smaller than its parent, so nothing is to be done. But in reality, it is not 5, it is 15, which is greater than its parent. So what we need to do is we need to swap it with its parent. So 15 will come here and 7 will come here. And now again, you will compare it with its parent. And again, you will realize that, hey, this again is greater. And you will swap again. So you will bubble the element from down till the top as far as it's possible to bubble it up. Is it making sense to everyone? Yes or no? Yeah, this is how insert operation works. Okay. So then comes delete root. You want to delete root. See, whenever you insert something in a data structure or delete something from a data structure, the final result should still have the properties of that data structure. So can you delete the root, which is 15 over here? How many of you can do that? You know, there can be several ways, but there is a very intelligent way to do it. And let me tell you what is that intelligent way. The first step is to swap root with last element. Okay. See, when you swap your root with the last element, what will happen is that 7 comes here and 15 goes there. Okay. Next step is to forget the last element. Okay, how do you forget the last element? This is an important question to ask. So I would say that, hey, in an array, there can be several elements, but you only track certain number of elements, which is in your interest. Let's say the size of array is n, but you have a variable s, which says that, hey, only these many elements are in my purview. Okay, so initially the value of s was 7 because there were 7 elements. And now after swapping your root with the last element, which was your first step, what you can do is you can do s minus minus. The moment you do s minus minus, this element gets out of your purview. Does it make sense? Yes or no? Right? Now, when this element gets out of your purview, then it looks like, hey, there is a root whose left and right are already max heaps. Because they are max heaps, so I can just do the same operation that I have been doing over here. So I'll compare it with its both children and swap it with the larger one. And then again, the same thing will be done so far it is possible to do. So this is just a 3-step process. The first step is to bring your root, which you want to delete, at the end, and then forget that element. Forgetting an element from an array is very easy. Especially forgetting last element is very easy. You can just do size minus minus. And then the situation will just be like how it was here. Does it make sense? How many of you understand how we have deleted? Okay, one of you is asking, can we start rebuilding from index 1? You do not need to rebuild things again, because if you rebuild, it will consume more time. So it's better to act intelligent as we acted over here. Yeah. Okay, so there is one more final operation which I want you guys to think on your own, and that is delete at a random index. So delete at a random index. Let's say somebody says delete this particular thing. So how do you go about it? So think of it, and again, the solution to this is present on your dashboard. Think of it, and you will be able to realize that. Is it clear? Do you guys get understanding of heap at least on a high level? Yeah. So next thing that I want you guys to write down as your homework is, when you go back, please go through the priority queue implementation in your language and learn how to use priority queues, and refer to your dashboard for any additional details. Cool, guys. So I'll just keep this much for today. We'll be meeting tomorrow again with some. So now maybe just one class is remaining, and we'll try to complete the leftovers in that. Okay. So bye, everyone. Have a good day.